This is our third video lecture over section 4.3 on binomial probabilities, and in this video we'll be looking at another calculator function, the Binomcdf calculator function. Before we talk about what it does, let's look at an example to motivate why we would need another calculator function. We've got one of our standard experiments here. A coin is flipped 10 times. Find the probability that the coin comes up heads 4 or fewer times. Let's go with our standard way of approaching these problems. We're first going to verify that this is binomial. We've got a fixed number of trials. We're flipping the coin 10 times. And in each trial there are two possible outcomes. The coin could either come up heads or tails. And so we've got those two conditions that I want you to check for each time. This also meets that condition of independence that I don't ask that you check for. So this is a binomial probability experiment. Once we verified that an experiment is binomial, my advice has been to make this list of inputs, n, p, and x. N is the number of trials in the experiment, p is the probability of success in any one trial, and x is the number of successes that you're interested in. We've already determined that n is 10, there are 10 trials. P and x are dependent on which outcome you consider to be a success, and since we're counting up the number of times the coin comes up heads, in my opinion, the easiest way to approach this is to make a success when the coin comes up heads. P is therefore the probability that the coin comes up heads in any one flip, which we've said many times is 1/2. You could also use 0.5. And now we come to the value of x. X is the number of successes you're interested in. And we actually have multiple values that we're interested in because we want the coin to come up heads 4 or fewer times. So any number of successes less than or equal to 4 satisfies our event. So we're interested in the x values 0, 1, 2, 3, and 4. All 5 of those values satisfy the event 4 or fewer times. One way to handle this is to calculate Binomcdf 5 separate times and then add those all together. And you can see I've got that on the screen here. Binomcdf of x equals 0, 1, 2, 3, and 4, all 5 cases. And we could add all those together. And we get our answer of around 37.7%, 0.377 if we rounded to the nearest thousandth. And I guess that's okay here, but there has to be a more efficient way, and there is. Because this situation of adding up multiple Binomcdf probabilities comes up fairly often, the calculator is actually programmed with a second calculator function that will do that automatically. And that's this new Binomcdf calculator function. Binomcdf of n, p, x is the probability of no more than x successes in n trials of a binomial probability experiment, where lowercase p is the probability of success in any one trial. Binomcdf from the previous video finds the probability of exactly x successes, one case, but Binomcdf will do the probability of no more than x successes, up to and including x successes. Another way to think of this is that Binomcdf is just the sum of a bunch of Binomcdfs. If you tell the calculator to do Binomcdf of n, p, x, it will start with Binomcdf of n, p, 0, then add on Binomcdf of n, p, 1, and it will continue adding those up until you get to wherever you told it to stop. X is where it will stop. Well, that's exactly the situation that we're in. We have a sum of Binomcdfs that we want to string together. Rather than typing all 5 of those in and adding them up, we can just use our new Binomcdf function in order to do this. This is Binomcdf of 10, 1/2, 4. One way to remember that the CDF function adds all these together is to realize that the C stands for cumulative. This is the binomial cumulative distribution function. So it's going to add all those up. It's going to accumulate them, put them all together. Let's run the Binomcdf function, and for our first example, I'll do it for both operating systems. In the newer operating system, you'll get that input screen. I'm going to leave all of this mess on the main screen so we can compare our two answers. We're going to access Binomcdf by pushing second and the vars key. We talked about this in the last video. Binomcdf is the choice directly underneath Binomcdf. That's why you have to be careful when you're scrolling. You want to make sure you select the right one. In my calculator, Binomcdf is choice B. If you have an older calculator, it might be choice A. Just make sure you pick the one that says Binomcdf. Again, with the newer operating system, you're going to get that input screen. The number of trials is 10, that's the value of n. P is the probability of success, that's 1/2 or 0.5. Make sure you put in a number between 0 and 1. You can't put in 50 for 50% because P has to be between 0 and 1. The x value that we choose in Binomcdf is where we want the calculator to stop. Binomcdf is always going to start at 0 and add up values of Binomcdf until the spot where you tell it to stop. Well, we want to start at 0 and end at 4. Let me push this out of the way for just a second. We want all of the x values from 0 to 4, and so we're going to tell the calculator to stop at x equals 4. We'll then paste this on the main screen. Then we hit enter. And notice that we get the exact same answer, but in a much more efficient way. We still get that 0.377-ish number. So the probability of getting 4 or fewer heads in 10 coin flips is around 37.7%. Let me redo this for those of you that don't have that stat wizard screen. Go back to the calculator. I'm going to push second vars. It's going to be in the same spot, either choice B, like it is in my calculator, or choice A. It's directly underneath Binomcdf. Select that Binomcdf option. 10 trials, probability of success is 1/2 or 0.5. And again, we want to stop at 4 total successes. Binomcdf of x equals 4 will tell the calculator to add up all of the cases from 0 to 4, which is exactly what we want. Hit enter. The difference here is that we didn't have the stat wizard, so we had to input n, p, and x separated by commas on the main screen, just like you do with Binomcdf. Now, a couple of things to talk about. First, when we ran into a situation like this in the previous lesson, we just used the complement. Why doesn't that work here? Well, the complement of 4 or fewer is 5 or more. So that would be the cases 5, 6, 7, 8, 9, and 10. We would stop at 10 because n is 10. And that's actually more cases than we started with. That's not going to be any easier. So the complement idea does not work here. It doesn't make things easier. It worked in the previous lesson because we were doing the complement of 1 or more, and that only leaves one case behind. That's a simple situation. Here the complement makes things worse. The second issue to address is that some of you might not think that it would be a big deal to type in those 5 inputs. So what? That's not that many options. It didn't really save us that much time. True in this example, but let's look at another. Approximately 67% of households in the United States have a pet. Suppose 100 households are selected at random. Find the probability that fewer than 50 have a pet. Now, you might already see where I was going with my previous comment, but let's go back to basics. Is this a binomial experiment? Well, we have a fixed number of trials. We've got 100 households. And in each trial, there are 2 possibilities. Either that household has a pet or they don't have a pet. And so this is binomial. We also get the independence here because of the random selection, but the 2 important parts that I want you to check are satisfied, fixed number of trials, 2 categories of outcome in each trial. Now we'll start to make our list of n, p, and x. N is 100, there are 100 trials. P and x are dependent on what you consider to be a success. We're counting up the people who have a pet, and so I would make a success a household that has a pet. That's pretty convenient because we're given the percentage of households that have a pet, so the probability of success will be the same as that percentage of households, 0.67. And now we finally get to my point. We want the probability that fewer than 50 have a pet. So fewer than 50 would be 0, 1, 2, 3, 4, 5, 6, 7, all the way up to but not including 50. It says fewer than 50, which would not include 50. 50 is not less than itself. So this is the cases. So this is the set of cases from x equals 0 to x equals 49. That's 50 independent cases. Even if someone really didn't want to learn a new calculator function like Binomcdf, you have to admit it's going to be way more efficient here. Binomcdf is built for this case. Remember, Binomcdf says, hey, you want to add up a bunch of Binomcdfs that start at 0? Just tell me where to stop, and I'll add them all up for you. The alternative to using Binomcdf isn't that nice. You're going to have to add up 50 cases. Let's just use Binomcdf. That's what it's built for. Just like I did with Binomcdf, I'm going to abbreviate BCDF for Binomcdf. N is 100. We've got 67% probability of a success. And again, all you have to do is tell the calculator where to stop. We want to stop at x equals 49. It knows to start at 0. Binomcdf always starts at 0 and increments by 1 up to your stopping point. So we want to stop at 49. Let's take this to the calculator. Second vars. There is a shortcut for selecting choice B. It's alpha and the apps key in my calculator. It's alpha and the button right next to the math key. That's a shortcut to selecting choice B. Binomcdf. For those of you that have the older calculators, if you need to select choice A, that's alpha and the math key, which I demonstrated in the previous video for Binomcdf in my calculator. We have 100 trials. The probability of success is 0.67. And we want to go up to 49. We don't want to include 50 because it said fewer than 50. Enter, and we get a really small probability. Notice that this is in scientific notation. That says move the decimal point 4 places to the left, so you're actually going to get 3 zeros, and we'll just stop at the 1.5. This is around 0.00015, which is around 0.015%. If you're trying to get a handle on how small this probability is, just count out the places. This is the 10th place, 100th place, 1000th place, 10,000th place, 100,000th place. So that's 1,500 thousandths. So the probability would be around 15 in 100,000. That would reduce to 3 in 20,000. Very, very small probability. It's much more likely that you would have 50 or more homes with a pet. And that makes sense because 67% of all households have a pet. 50 out of 100 is only 50%, so we're asking for the probability that less than half of the homes have a pet. It's much more likely that at least 50% would have a pet. So it's not that surprising that we get this small of an answer. Our next example has a classic trap in it, so you got to make sure you read carefully. It is estimated that around 13% of drivers do not have insurance. Suppose 30 drivers are selected at random. Find the probability that no more than 20 have insurance. If you're not paying attention, this sounds like a straightforward problem. But there's a pitfall to this one that we have to talk about. First things first, let's verify that this is binomial. We're selecting 30 drivers, that's our fixed number of trials. And in each case, there are two possibilities. Either that driver has insurance or they don't have insurance. So this is binomial. We'll make our list of values n, p, and x. N is 30. We've already determined that. And here's the part where some people are going to get into trouble. A lot of people will take that 13% and immediately write it in for p. But you have to remember that's dependent on what you consider to be a success. And here, I would not make my probability of success 13% because of the way the problem is worded. What is my success? Well, I've mentioned that I like to make a success the thing that you're counting up in the problem. And if you read carefully, you see that we're counting up the people who do have insurance. I would make a success a person who has insurance. Is that the only way to do the problem? No, but that's the way that I would approach this because that's what we're counting up. I think that's the easiest way to do these. That 13% is not the percentage of people who do have insurance. That's the percentage of people who don't have insurance. So what is the probability that somebody does have insurance? Well, it's 1 minus the 0.13. It's 87%. That's that complement rule from before. I did that because of what I chose to be a success. And you might say, well, that seems complicated. Why would you do it that way? Because it makes x easier to find. When I go to list what x values satisfy our event, I can just use the description that's given. No more than 20 have insurance. So I just want to make sure I take all the x values that are not more than 20, which would be from 0 to 20. 20 is not more than itself, so you would include 20. This is what Binomcdf is built to do. So I just have to give the correct inputs. N is 30. P is 0.87 because I chose a success to be somebody who does have insurance. and I just need to tell the calculator to stop at 20 successes. Let's run this in the calculator. Second, vars. I'm going to scroll to choice B to be careful here rather than selecting it with alpha. Feel free to use the alpha shortcut. 30 trials. Our probability of success was 0.87 because we chose a success to be somebody who does have insurance. 20 successes is the maximum. Telling the calculator to do Binomcdf of x equals 20 is instructing the calculator to add up all of the PDFs from 0 to 20, which is exactly what we want. And we get another small probability, but at least it's not in scientific notation. Rounding this to a few significant digits, oh, that's kind of fun, 3, 4, 5, 6, that's where I'll round it to. So this is about 0.003456 or 0.3456%, right? That's less than 1%. It's pretty close to 1/3 of a percent. So very small probability that no more than 20 have insurance. It'd be much more likely that more than 20 have insurance. And again, that makes sense because 87% of people have insurance. And so the more likely scenario is that we have closer to 87% of our sample having insurance. So the small probability isn't surprising here. The probability of winning a prize on a specific scratch-off lottery ticket is 23%. Suppose you buy 15 tickets. What is the probability that more than 12 are losers? Now, I threw in a little bit of emphasis there. I put a little stank on that word losers, but I hope you notice we have that same issue we had before. We're counting up losing tickets, but we were given the probability of winning, so we're going to need to be careful about how we choose our success. This experiment is binomial because we have a fixed number of trials. We're buying 15 tickets, and in each trial it's either a winner or a loser. So we've got the characteristics of a binomial experiment that I ask you to check for. N is 15. P and X are dependent on what you consider to be a success. And again, I know there's a temptation to choose P to be 0.23 because that's the probability that's given. But I want you to notice that we're counting up the losing tickets. And so I would make a success a ticket that loses. The reason I do that is because it makes it easier for us to come up with our X list. Coming up with P does take a little bit of work, but in my opinion, it's much easier to adjust the value of P than it is to adjust the value of X. The probability that a ticket wins is 23%, so the probability that a ticket loses is 77%, 0.77. That comes from doing 1 minus 0.23. We want the probability that more than 12 tickets are losers. Well, the successes are the ones that lose, and so more than 12 would not include 12. That's 13, 14, and 15. We stop at 15 because there are only 15 tickets being sold. Your calculator is not built to start at 13 and end at 15. So Binomcdf can't be used on this list on its own. You could argue that this list is small enough that you could just do 3 instances of Binomcdf and add them together. But I want to show you the alternative, and the alternative is to use a complement. I'm going to start abbreviating complement COMP since we're using it so often. What is the complement of more than 12? It's not less than 12. The complement of more than 12 is less than or equal to 12. So 0, 1, 2, all the way up to 12. Between x and the complement, you should have every whole number from 0 to 15. X has the numbers 13, 14, and 15. The complement needs to have all of the other possible cases, which would be the ones that are less than 13, less than or equal to 12. So 0 through 12 in our complement. Now that's a longer list, so it seems like we've given ourselves more work. But the beautiful thing is that this list is what Binomcdf is built to do. I can find Binomcdf of 15, 0.77, 12 with a single calculator function. You just have to remember that that's not the probability that we want. That's the probability of the complementary event. This thing right here is the complement. Let me put this in this spacey color. This is the complement of our event. To get our probability, we're going to have to subtract that from 1. Anytime you use the complement to find the probability that you want, you have to subtract from 1. Why did we use the complement? Why would we put ourselves in a spot where we have to do this extra step? It's because the complement can be done in a single calculator function. Again, you might argue that this isn't a long enough list to warrant using CDF, and I can't argue with you there. but I'm trying to demonstrate how we can use a single calculator function for when those lists are long. Let's throw this in the calculator. So I'm going to type the 1 minus first and then access second vars. It's Binomcdf 15, comma, 0.77 using the probability of getting a losing ticket, comma 12 because that's where the complement ended. And we get around 0.294, really close to 30%, 29.4%. Something that happens almost 30% of the time couldn't be considered rare. So you shouldn't feel cheated if you get more than 12 losers. A lot of people have this visceral reaction to getting a bunch of losing lottery tickets, and they think that the lottery is cheating somehow. But you could buy 15 tickets and get 13 or more losers. It wouldn't be that weird of an occurrence. So there are a couple places here where students give me pushback on my approach. They don't like that I chose the 0.77. Some students don't like that I didn't just use the 0.23 that was given in the problem. But again, my rationale is that it's easier to count up the losing tickets than the winning tickets, in my opinion. You might not feel that way. Your brain might be wired different than mine, and you might find it easier to count up the winners than to adjust the value of p. That's fine. Do the problem that way. We should get the same answer. The other place I sometimes get pushback is that my list here wasn't long enough to warrant this extra complication of having to do a 1 minus. I hear you. That's a valid criticism. Let's look at another example. A tourist trap clothing store hands out 1,000 coupons redeemable for a free shirt. Right? They're trying to bring people into the store, so they comb the beach and they hand out these coupons to the tourists, hoping to get them into the store. From experience, they assume there is a 5% probability that one of these coupons will be redeemed, so they only printed 60 shirts for this promotional event. 5% of 1,000 is 50, so they built in a little extra buffer. They printed 60. But it is possible that that's not enough shirts. So let's find the probability. What is the probability that the store will run out of the freebie shirts in this promotion? Right, they printed up some cheapo shirts to hand out, and they only printed 60 because their expectation is that 5% of the people will show up. So what we want to do is see if they're going to run out of shirts. Because if they don't have enough shirts, that's going to make the customers who showed up mad. It'll feel like a trick. It's a trick anyway to get them into the store. But the customers will feel duped and they'll get bad Yelp reviews, and who knows what will happen from there. So they're really asking themselves, is printing 60 shirts a safe number, or should we print a few more just in case? How likely is it that we'll run out of these shirts? Is this binomial? Well, there are a fixed number of trials because they're handing out 1,000 coupons. And for each coupon, there are one of two cases. It will either be redeemed or it won't be redeemed. So this is binomial. It meets those two conditions. Let's make our list. I'm going to have to do this on another slide because I didn't give myself enough room. There are 1,000 trials. P and X are dependent on what you consider to be a success, but we don't have that same issue that we had before. There's a 5% probability that a coupon will be redeemed. That was given in the problem. And we're finding the probability that the store will run out of shirts, which means that we're counting up redeemed coupons because we're counting up the number of shirts that we hand out. So a success is going to be a redeemed coupon. We know that the probability that a coupon is redeemed is 5%. That's 0.05, not 0.5. 0.5 is 50%. And now we have to put a little bit of thought into what it means for the store to run out of shirts. It doesn't explicitly say how many successes that is. Some of you say, well, they'll run out of shirts if 60 people show up, so X is 60. That's a good start, but that's not the only case in which they run out of shirts. If 61 customers show up and try to redeem this coupon, they'll still run out of shirts, but now they'll have an angry customer. That's another case to consider. And if 62 people show up, they've run out of shirts. We don't want to consider just the most extreme case. We want to consider all of the cases where they run out of shirts. So from 60 on. In the previous example, our X list only had 3 cases. Now you've got over 900 cases. Even the most stubborn person would have to admit that a complement's going to be the best way to do this. Let's talk about how you would figure out the complement both in words and then just using a mathematical rule. The event we're interested in is that the store will run out of the freebie shirts. So the complement of that will be that the store does not run out. And in what cases would they not run out? Well, if fewer than 60 coupons are redeemed, then they won't run out. So that would be from 0 up to 59. They run out of shirts when they hand out the 60th shirt. So in words, the complement of running out of shirts is not running out of shirts, and then we can figure out the complement. Or you can do this numerically. Remember that between X and the complement, you have to have every case from 0 to n, from 0 to 1,000 in this particular example. X hogged all of the numbers from 60 to 1,000, so the numbers left over for the complement go from 0 to 59. Now that's a long list of 60 numbers. That's still going to be a pain, except we have this new Binomcdf function that can handle that. N is 1,000, P is 0.05, and we just tell the calculator to stop at 59. You just have to remember that this is that complement, not the original event, and so we subtract from 1 to get the probability that we want. So I'm going to start by typing the 1 minus. I like to type that in first so that I don't forget to do it. A lot of students will give me the right setup with the 1 minus, but then they forget to actually do the 1 minus in the calculator. And I'm prone to do that too. So I like to type it right away so I don't forget. Second vars, I want Binomcdf because we're adding up a bunch of cases in the complement. There were 1,000 trials. The probability of success is 5%, 0.05. That's the probability somebody comes to get one of those shirts. And we're going to subtract off all of the cases up through and include 59. And let me just talk about the logic here again. This Binomcdf part is finding the probability that they don't run out of shirts, but we want the probability that they do run out of shirts, so we're subtracting from 1. That's not a negligible probability. If we round this to 3 significant digits, that's 0.0867. There's an 8.67% chance that they're going to run out of shirts. That's not a super high probability, but as I said, it's not negligible. That's not an ignorable amount of the time. They might want to print more than 60 shirts just to make sure. Let's do one more. A machine produces parts used for assembling a small electronic toy. It is assumed that 95% of these parts are in working condition. Find the probability that in a random sample of 12 parts, at least 2 are defective. Is this binomial? We have a fixed number of trials. We're going to select 12 parts and inspect them to see if they work. And in each case, there are 2 possibilities. It either works or doesn't work. It's in working condition or it's defective. So this is binomial. N is 12. P and X are dependent on what you consider to be a success. And I hope you noticed that we have that same issue. We were given the percentage that are in working condition, but we're counting the ones that are defective. You have to make a choice what you want to make a success. There isn't a wrong choice, but you have to make an active choice. I hope I've made clear what I would do. We're counting up the defective ones, and so I would make a success a defective part. That's what we're counting up. That's what I would consider to be a success. No, that probability isn't given in the problem, but it makes writing out the list for X easier in my opinion. You could alternatively make a success a part that's in working condition, and then the value of P is given, but then you have to put in the effort to figure out what the X list is, because it won't be the same. You couldn't use the at least 2 description here. If you don't like the way that I'm doing this, I encourage you to try to do it the other way, because if that makes more sense to you, I want you to do it that way. I'm going to run with my choice, which is a success is a defective part. If 95% are in working condition, then 5% are not. Yes, I had to do a little bit of extra work there, but now I'm looking at the probability that at least 2 are defective, and at least 2 means 2 or more. So that's 2 through 12. I stop at 12 because n is 12. That list does not start at 0. Binomcdf can't be told to start at 2 and end at 12. Binomcdf always starts at 0, so I need to use the complement here. We fall back on the complement when our list is something that our calculator cannot handle. We did that in the previous video, and we're doing that here. The complement is nice and short. I'm still going to use CDF to calculate that probability though, but that's not the probability that we want because that's the complementary event. So I'm going to subtract from 1 minus that to get the probability that we want. Okay, let's put this in. 1 minus, second bars, Binomcdf, 12 trials, 5% probability of success because I chose a success to be a defective one, and our complement ended at 1. So we get about 11.8%. This is about 0.118, which is 11.8%. This is like a quality assurance problem. We're assuming that 95% of the parts are in working condition, but if you took a sample of 12 parts and got 2 or more defective ones, so we ask ourselves, is that weird? Are we really producing parts that are in working condition or not? We'll talk about the benchmarks that we use for that in a later section. Okay, so this ends our introduction to the Binomcdf function. If you have any questions, please don't hesitate to contact me.